Introduction to graph theory. So what is the graph? A graph is a non-linear data structure consisting of nodes and edges. So edges is your lines that are your edges, and nodes. So nodes are sometimes also referred to as your vertices, which means your numbering over here 0, the numbering 0, 1, 2, 3, 4 are nothing but your vertices, and the edges are the lines or the arcs that connect any node. The edges, these lines which connect your vertices are nothing but your edges. I have same as described in the example. So more formally, a graph can be defined as a graph consists of a finite set of vertices or nodes and a set of edges. So which means it's a collection of vertices and collection of edges which connect to form a graph is nothing but your vertices and edges. Okay, so let's see where can you find graphs. So graphs are used to solve many real life problems. Graphs are used to represent networks. Your networks like such as your LAN, WAN and your MAN and that networks, which is helpful in connecting. Example, like one person can connect to many devices, can be your Wi-Fi for example. So the networks may include paths in the city or telephone network or a circuit network. Okay, so the graphs are also used in social networks like your LinkedIn, Facebook, like which is for example in Facebook, each person is represented with a vertex. This is also true, or a node. Each node is a structure and contains information like person ID, name, gender, locale, etc. etc. So here, if you take an example of a Facebook, your Facebook ID consists, your Facebook even consists of a structured information like a person. One, it has a person and it has ID and it has your name. So these are also a collection of networks, you can say, where we can find graphs. So I have few definitions of graphs and subgraphs, or you can tell properties or few definitions or simple examples of how you can classify graphs. So a simple graph, which means it's nothing but a graph without a self loop and parallel edges, is said to be a simple graph. Example, your graph which is having square or a 4 dot, for example, this is your edge and this is your vertex as described in the image. This is said to be a simple graph with 4 vertices and no intersections or loops, such way. Okay, even a tree structure, this diagram is also called as your tree structure, which is also a simple graph with nodes and with you tell these are the parent node and these are the child nodes, and this is a parent node and these are the child nodes. So this is also a simple graph. Next is your multi-graph. This is what I was talking about, your loops and your multiple edges. So multi-graph is a graph that consists of either multiple edges or loops. So we can consider a multiple edge to be a line from a vertex x to y. Suppose if you take an example, this is your vertex and this is your vertex y. This is your vertex x and this is your vertex y. On the other hand, we can consider a loop to be an edge that wraps around back to itself. For example, multiple edges can also contain number of lines passing from your x and y. Like your x goes to y, your y can also come back to x. This is nothing but your multiple self-looping graphs, which is having loop. Even this is also called a graph, multi-graphs as an example, where it has several loops and it also has multiple edges. So this is also an example of a multi-graph. Next is your diagraph. So digraph is nothing but directed graph, which means it has a direction. It shows a direction. Suppose this is your x and this is your y. There is a direction. That means your edge is going from x to y. This also you can consider as an example. So let's see the definition. A digraph is a graph D. You represent digraph with D. Let me write it clearly. With D. That contains directed edges. Is also called arcs instead of regular edges. So we note that a directed edge or an arc contains some sort of direction from one vertex to another vertex. Just like I said, if this is your x and this is your y, you have a direction to it. So if you see, look at the other examples here. This is also a directed graph. Suppose this is A, this is B, and this is C, and this is D. So you have a direction of A to B, and B is going to C, and B is also going to D. In the similar way, we have another example. So next is your subgraph. So what is a subgraph? Subgraph is denoted with S of a graph G whose vertex set V of S is a subset of vertex set V of G. Here V is your vertex. Let me write that clearly. V is your vertex. Is a subset of vertex V of G. Suppose this is your V of S and this is your V of G. We mainly denote graphs with G as a graph. Subset is nothing but the graph. If you take the example of the main graph, which is V of G, this portion is being duplicated or is being taken away to form subset of graph. So this V of S is definitely a subset. The V of S is definitely a subset for V of G. So if you look at the definition, that is V of S, the symbol is the subset symbol. V of S is subset for V of G, and whose edge set E of S is subset of edge set V of EG. That means even the edge. Your edges are also the same as well as the set vertices of V of G. So which means your edges, your vertices as well as your edges. This is V of yes, even E of S, it should be a subset for your V of G. That is your edges. So here if you see, suppose if this is I'm taking this example as A, B, C, and this is your D, E, F, and D. So you have vertices A, B, C, D subset. I'm writing a subset for that also. A, B, C, and D, which is nothing but your vertice. Similarly, even the edges should be of the same number, which means A of C, A of C. Let me take the different color. A of C, A of C, A to B, A to B, BD and BD, C of D and C of D, which means this total forms to be a subset. So let's look at the next one. Basic properties of a graph. So if we see the basic properties of a graph, distance between two vertices. So what is the distance between two vertices? So distance is basically the number of edges in the shortest path between the vertex x and vertex y. If there are many paths connecting two vertices, then the shortest path is considered the distance between the two vertices. The distance between two vertices is denoted by d of x and y. So this is an example. I'll let you know with an example. Suppose if you want to find the distance between the vertex B and D. This is your B and this is the D. then first of all we have to find the shortest path between B and D. So there are many paths from the vertices B to D. We can even take B to D. So first is B, C, A and D. So we can traverse B to C, C to A and even A to D, which is the length of 3. And you will even take the shortest path, that is B to D, which is very closer, and that is 1. You can even traverse from B to A and A to D, which length 2. And similarly, the vice versa for B to C and C to D, which is also 2. And similarly, between B, C, A and which we have already discussed in this case, hence the maximum distance between the vertex B and D is 1. The minimum distance between the vertex B and D is nothing but that's the shortest path. So this is nothing but the distance between two vertices is basically the number of edges in a shortest path between the vertex X and Y. So this is nothing but your distance between two edges. If you want to traverse from B to A, for example, the shortest path can be B to A, which we have seen upon the diagram. So we even can traverse this way too. But distance, this is what the meaning of distance between two vertices. So next is your eccentricity of vertex. So what is eccentricity? Eccentricity of vertex is the maximum distance. So it is a vice versa, the distance between a vertex to other vertices. So it is denoted by E of V. To count the eccentricity of vertices, we have to find the distance from the vertex to all the vertices, and the highest distance is the eccentricity. So I'll take this and I will show this to you in the form of an example. So here, if we want to find the maximum eccentricity of vertex A, suppose if you want to find the maximum eccentricity of vertex A, then the distance from A to B is, that is AB, which is 1, which means only one line or your edges is being traversed from the distance of a vertex A. So if you want to traverse from A to C, your A to C is this way, which is also 1. The distance we are traversing, like A can be traversed from, if you want to go from A to E, A to E, so C, A to D, A to B, A to E, that way. So we're checking the eccentricity from the vertex A. So A to F, A to F, we have two ways, that is ADF as well as ACF, the shortest part, ACF and AD, that is DF. So the A to D is also 1. The distance from the vertex of A to E. Now traveling from A to E, we can either go from AB to BE, or we can even go from AD to DE. A to G is also the same. You can even take ABEG, or we can take ACCF, FG, that way. Anyway is also possible. So if we take the maximum eccentricity of vertex A, the maximum vertex eccentricity is nothing but E, which is traversing to G, to all the other vertices. So similarly, the maximum eccentricities of other vertices. So this is just calculated for A. This is how you calculate for A. So similarly from B, we have calculated the maximum eccentricity vertices as 3 and so on. I have calculated and I have written as shown. So coming to the radius of a connected graph, the radius of a connected graph is the minimum eccentricity from all the vertices. In other words, the minimum along all the distances between a vertex to other vertices is called radius of a graph, which is denoted by R of G. So for example, I'm taking the previous set of examples that I wanted to take in this example also. The maximum or the minimum eccentricity for the vertex from D. So if you see from B, C, D, E, F, the minimum eccentricity is your D, which is E of 2. So that is what is nothing but your radius of a connected graph is the minimum eccentricity. Okay. Next, diameter of a graph. So the diameter of the graph is the maximum eccentricity. This is the vice versa of your radius of a connected graph, which we calculate the minimum eccentricity from all the vertices. But here diameter is the maximum eccentricity from all the vertices, which means it is denoted by d of g. In other words, maximum among all the other distance between vertex to all the other vertices. So for example, I've taken from the previous example. If we see all the eccentricities of vertex, we see that diameter of the maximum of those eccentricities is diameter is g, which means 3 d of g. 3 is a maximum eccentricity, which means your b, c, f, g can also be your maximum eccentricity from the vertices. Similarly, this diameter, to find a diameter of the graph, we take the maximum, but to take the radius, we take the minimum. Okay. So next is your center point. So if the eccentricity of a graph is equal to radius, see, eccentricity of a graph is equal to radius, and it is known as central point of a graph. Or if r of v, your r of v is equal to eccentricity of v, your radius of vertices is equal to your eccentricity of vertices, correct? And v is central point of g. So from the previous example itself, d is a central point of graph, that is e of d is equal to r of d as well. So which means your center point, the lowest, the minimum, when we take, the minimum is pointed in the between, which is your 2. So this is your center point of the graph, which is calculated from the eccentricity of a graph. Okay. The simple properties and notations. Next comes your circumference. So circumference is nothing but the total number of edges in the longest cycle of graph is known as circumference, which is denoted by g. Circumference of g. For example, the circumference is 6 when derived from the longest path. That means we had taken the path. Suppose if we take A to C, C to F, F to F to G is this way. F to G, G to E, E to B, and B to A. So which means starting from one vertex and completing back to its vertex. Okay, this is your maximum longest path that is derived. Okay, another path, that's A to C, C to F, F to D, and E to B, and again E to A. You can take any path. So the total number of edges in the longest cycle is your circumference of G. So next is your girth. Girth is nothing but the total number of edges shortest cycle is opposite to the longest path, that is A to C, C to F, F to D, and F to D. That's the shortest cycle from your point of A. In a similar way, we even have A to B, B to E, E to D, and E to A, which means traversing the shortest path to reach the destinations.